Hello and welcome back to the Hyperthesis and Happy New Year! We are in 2024 now, the first episode of 2024. My name is Feely.
I'm Patrick.
And I'm Liam.
All right, we are back. Well, I think looks like most of us, all of us are back from vacation. And yeah, to me, it was pretty good. Got to go to the country. And now I'm back in the good old city. And well, some people wouldn't say that it's much of a big city, but got to prepare myself for the upcoming semester. That's going to be fun. But well, today we're going to be talking a bit about quantum computers and how it works, kind of from my perspective. But does anyone else have things to say from your vacation?
I don't know if Patrick does.
Yeah, I mean, it was a relaxing vacation and going to just try and delve into 2024 with a lot of hard work to try and get things published. And there's going to be quite a bit of travel to conferences and field work and all that. But I'm sure we'll be talking about that as they come by.
Nice. Mine was super relaxed, and I stayed in Hamilton for Christmas, and it was really foggy for some reason. Very not snowy Christmas and New Year's, which is kind of lame, but also I didn't have to shovel, which was good.
Yeah, the weather is different for sure, right? Because I think we mentioned last time too, people would usually go skating on the lake, for example. And here, even in a little bit more north, it's still pretty warm in a way that is the ice sometimes not thick enough for people to safely skate on it, or sometimes you couldn't put cars on it. I remember you used to be able to drive, I think, from Kingston to like Wolf Island or something, but they canceled that years ago.
Yeah, when I was living in Ottawa, the Rideau Canal, they turned it into a big like rink so you can skate to work and stuff. It's pretty cool. And they have all these like food stands on it, and trucks will drive down the canal. Not just you can't just go on it on your own vehicle. They're like government workers or whatever who are like maintaining the ice, but they'll drive just down the river on their truck on the ice. And I remember skating on the ice as a truck drove by, and it made me a little bit uneasy. I was like, oh, it's a heavy vehicle next to me. But when the ice
You
gets
must
really
feel safe though.
yeah, when the ice gets
Like,
really thick, it's safe, and they monitor it super well at like all these different points. So I
Yeah,
think
I saw the news. I think a couple guys passed away from, falling into the ice was trying to skate. That's unfortunate.
yeah, I don't think the government wants to have a bunch of people falling into the Rideau Canal on their hands, so they monitor it pretty well. But each year there's less time to skate on it, which sucks. But so I'm glad I got to. But yeah, so I think just as a warning, I think I developed a little bit of a cold. So my voice is a little raspy and I might cough a few times, but we'll see. Maybe the more I talk, the worse it gets. So I better just get into our intro topic today, which I thought was relevant because it's the physics of popping champagne bottles open. I found this paper by some Austrian physicists in the Archive preprint journal. It was published on December 19th, 2023, and was titled Simulating the Opening of a Champagne Bottle. So this paper claims to finally clarify how the physics of popping open a champagne bottle works. And I chose it because I really like everyday, or at least what I call everyday physics. So stuff that you think we might understand really well, but turns out there's some deeper science going on. And although you might not be popping open champagne bottles every single day, it was around Christmas and New Year's. I figured that's a time of year when it happens the most, probably, at least here in Canada. I popped a champagne bottle open for New Year's. So when I saw the paper, I was like, oh, I got to read this and probably talk about it in the podcast. So yeah, at first glance, popping the cork off of a champagne bottle or any other bottle with a cork that's pressurized, it seems like a pretty simple phenomenon. So there's liquid and gas in the bottle. It's at high pressure. So when the cork gets opened, that high pressure shoots the cork outwards and creates a powerful popping noise due to the compressed gas in the bottle. But it turns out that there's this complex supersonic physics happening during the popping process, which we were unaware of before. And there's been experiments in the past that have studied this with high-speed cameras, but there was no mathematical theory or numerical analysis behind it to understand what was going on. That's something that happens in physics a lot is, well, I think you have one of two things. The first one is that you come up with a theory and then you do an experiment to test the theory. But the other thing is that you just do an experiment and you write down some results and you say, this is what happened when we did this. And then someone develops a theory to describe what's happening so you can actually understand what's going on with the physics. So this was one of these things where the experiment came first, and this paper kind of tackled the theory of it and studied some numerical simulations. So this paper kind of closed that gap. So when you pop the cork off a champagne bottle, the cork itself flies off at relatively low speed. So maximum, it can reach around 70 kilometers per hour, which is about 20 meters per second. So that's pretty fast. But I think it only reaches this speed for a short time. So it doesn't whiz across your house that fast. It probably just reaches that for a fraction of a second.
Well, the cork is pretty light too, right? Like so it's much speed, but not that much momentum. So if it hit your body, you'll be fine. But just don't let it hit your eyes, right? Could go really wrong. And yeah, I think I did have a champagne to pop on New Year, so I think it's pretty common.
Yeah. So that's why I think this is a good time to talk about it, because a lot of people have recently popped a champagne bottle, so they have it fresh in their memory. So even though when you pop this cork off, it moves pretty fast, but it's not that fast. It's not these crazy speeds. Turns out that the gas itself within the bottle, that as the cork pops off, the gas flows out really fast, actually. This pressurized gas within the bottle, it can actually reach up to 400 meters per second, which is faster than the speed of sound. And again, it's over a very tiny period of time that this gas flows out. I forget what it is, but it's a fraction of a second that it reaches this 400 meters per second, this supersonic speed. So when it moves this fast, this gas jet creates a shock wave, which carries the cork. It creates a shock wave between the cork and the bottle as they're separating. And we've talked about shock waves before, but just as like a little refresher, a shock wave is this propagating density wave that carries energy, and it propagates through a medium just like any other wave. So like a wave propagating through the ocean, for example. But unlike regular waves, shock waves have this abrupt, nearly discontinuous change in their density, pressure, and temperature. So the point where this discontinuity occurs is called a Mach disk. And this is exactly what happens when you have like a jet, so like a fighter jet flying through the air at supersonic speeds. It's moving faster than the speed of sound, so it creates this cone of sound behind it, this shock wave. And when the shock wave hits you, it's just loud, really loud boom. It's because the sound waves didn't gradually hit you, it hit you with as like a wall, this wall of density. Something else we know about gas is it expands, because when you uncork this bottle, all the gas rapidly shoots out, so the gas is expanding. So that its density decreases, is that when the density of a gas decreases, its temperature lowers and it cools down. And an everyday example of this is a spray can, like a spray can of paint or air that you use to clean off computers. When you spray it, the can gets really cold because the density of the gas inside it is reducing really fast, so it cools down a bunch. So this also happens with the champagne bottle when the cork pops off. As the gas rapidly shoots out, particularly around the neck of the bottle, it becomes less dense and can actually reach temperatures as low as negative 130 degrees Celsius. And again, like the really fast gas coming out, it will probably only reach negative 130 degrees negative 130 degrees Celsius for a very short time period. But it's long enough that it can actually create these little crystals in the air. It can create dry ice. when you pop the cork off, you actually see this kind of like smoke that comes out. Those are the crystals that have formed in the air due to this really, really cold temperature for a brief second. And depending on the initial temperature of the champagne and the gas within the bottle before it's popped, these ice crystals can have different sizes. So if it's like room temperature champagne and it pops, the ice crystals will form with some size. And if it's refrigerated champagne, they'll be smaller or bigger. I forget which. But in principle, you can look at the color of this gas that forms, so the smoke that comes out of your champagne bottle, and you can actually determine what the temperature of the champagne was beforehand. Because depending on its initial temperature, they'll be a certain size and they'll reflect light differently. So they'll have different colors.
So basically, the smoke or like vapor you see, like a like steam like that come out of champagne, those are the effects from popping, not from the champagne itself, right? They're not really smoking the bottle neck, but what you see is actually if you pop it well, that happens.
Well, it's because of the gas in the bottle expanding so rapidly that it gets so cold that some of the water in the air freezes. So it's not like the champagne itself coming up, and it can cause all these things. So I think sometimes when the champagne bubbles, sometimes champagne like overflows when it pops. I think that's actually partially, well, it could be from a few things. It could be from the carbonation, if you shake the bottle beforehand, for example. But I think some of those ice crystals can actually fall into the champagne and cause it to decarbonate as well.
That's a skill issue.
Yeah, skill issue. I'll have you know that my cheap $20 bottle of champagne did not overflow when I popped it.
Well, the thing is, I think the proper way to do it is a lot of people try to just launch the cork into the air, which is fun, But what I do is basically twist it a little bit, like put your palm over it so it doesn't pop everywhere, and just pop it and just pour and drink it like a normal person, I guess. But you don't really need to shoot it because there's a risk of breaking the cork, and you get the rest of the cork stuck in there, which is terrible.
Yeah,
I do believe the proper way to do it is using a saber.
Yes,
which instead of popping the cork itself, will break the glass, and then I believe.
Yeah,
it just breaks the top, kind of like
that's what
the fancy way of getting wine out of the bottle.
It's not like you cut the head, right? You run sabers to the tip, and that would pop the cork off. Yeah, I heard of that, and I think I saw that. But I think it's more like very special occasion. I think you do it for weddings to be fun, but like you're, every day, it's like, oh, we're gonna have champagne today. Let me go grab my saber. That's gonna be a little strange.
Yeah, I don't own a saber, so I'd have to like rent one or find one somewhere. And I think if you're good at it, you just get the cork off. But if you're bad, you break the bottle. I don't know. Maybe you're supposed to break the bottle. Rich people are weird, man. They have weird traditions. I don't know what they are.
So I've just looked this up super quickly, and you are actually supposed to break essentially the top portion that contains the cork off the bottle. And this is something that's also done with wine, but that's a proper method. It's quite tricky to do because you're kind of catching the top lip of the bottle, and then it breaks in a certain place. But there's been many a viral video that's people just shattering the bottle because they haven't sabered it, as the term is, correctly.
Well, the thing is also, if you have really aged wine, right? So the cork is a little damp and not as new. So you might want to get rid of that entirely. But for like younger wine or sparkling wine, I don't think that really matter. A lot of cork these days are not even real cork. They're just plastic. It's not gonna, make a difference if you leave. There's no wood residue left on the edge because sometimes it's not even wood. But I think, and one thing to note that too is like when we say champagne, a lot of people be, well, I don't know if it's a lot, but it's supposed to be that sparkling wine from the region of Champagne in France, right? So if it's not from Champagne, it's not champagne, it's just sparkling wine, but we just use it as a normal, sparkling white wine thing.
I learned that about, I'll get back to the physics in a second, but it's the same with tequila as well. Tequila is like a specific place in Mexico that it's like the tequila is named after. So anything that's not real tequila from tequila is like some knockoff brand. It's the same with champagne. Champagne that's not from the specific place in France is it's like knockoff champagne. But anyway, side note. So just to kind of conclude, so what did the researchers do? I just listed a bunch of facts. A lot of the stuff this is what they learned from their theory and the experiments. But the researchers made simulations based on solving fluid mechanical equations of motion. So, like, I think they took the Navier-Stokes equations. They ignored viscosity, so you get some Euler equations for those people who know fluid mechanics. And they found that their theoretical results agree very well with the experiments. So they found that this audible pop noise that happens when you pop the champagne cork off, it's not just from the fact that the air is, or the gas inside is rapidly depressurizing. It's not just from this supersonic gas escaping. That's one half of the story. But the other half is that it's from the cork itself. So when the cork is compressed in the bottle, it has some diameter, and that diameter is compressed so that it's the width of the neck of the bottle. But when it pops out, the cork expands a little bit very rapidly, so its edges kind of move outwards and its diameter increases a tiny amount. But as it pops out, it kind of increases in diameter very suddenly and rapidly that it creates a sound wave. So part of the pop sound actually comes from the fact that the cork suddenly expands a little bit. And they did some math to model that. So they had a theory, and they found that this is you can't ignore this if you want to fully understand where that pop noise comes from. And additionally, they also said that even though this is like a fun little everyday physics model, the research and the numerical stuff they developed, it can also be used for other problems, such as firing bullets out of guns or for rocket launches, for example. So when a rocket shoots up into space, these are all different cases of situations where you have a very solid object, like a gun or a rocket ship or a champagne bottle, interacting very strongly with very, very fast-moving gas flow.
Well, I mean, I think it's super useful in like firearm, for example, right? Because a lot of modern firearms are gas operated, like the AR-15, for example. It has literally gas tube running back to basically pressurize certain part.
Even in like the engine of a car, for example, you have very fast-moving pressurized gas like in your cylinders, and although that's different, but like I wouldn't be surprised if there's some application there or something that we don't fully understand there that this could be used to understand better.
I'd also be interested to see how this kind of thing could apply to more advanced, I guess, artillery, such as railguns, which I believe we've talked about before long, long ago. But one of the big issues with railguns is that you have this hunk of metal that's being accelerated so quickly that when it meets the outside air, it's just kind of shredded because it's going so fast. So I'm curious if there's something from here that could be used to kind of dictate whether the shape of the projectile or even just how it can interact with the gas flow.
Yeah, that's a very interesting problem too, because the railgun use completely different mechanism of acceleration, right? Because normal cartridges explode and give off a lot of pressure and gas pressure to drive. That's why the longer the barrel, the faster the bullets goes. Technically, right? Well, there's a limit to that. But railgun is the opposite almost, because the longer, well, actually it's the same. The longer you can accelerate, the faster it goes. And there's a question of, well, what about the gas? Should you make the chamber vacuum, like the barrel vacuum, and then it hits the outside air, or should we have inside highly pressurized gas? Who knows? I mean, I'm not expert on railgun, but I think we should move on to the main topic for now. Unless Liam has some lasting words.
Nope, that's it.
All right.
I thought it was neat.
All right. Thank you, Liam, for the intro topic. So, over the break, I took a little bit of time to look up quantum computers just for my peace of mind, because it bothered me a bit because I never really understood it. I'm not sure if I understand it now, but perhaps you guys could correct me if I'm wrong in certain places. Well, I try to think about why quantum computers are important, or why is it such an advancement compared to classical computer. But people still say it's not gonna replace classical computers. It's kind of a little bit contradictory, but it's not really. But when you first hear about it, when I first hear about it, it's a little bit of contradictory, right? Oh, it's gonna be the new thing. It's like, well, how car replace horse and buggies, right? Like, well, you don't see people use horses and buggies anymore. Most people, but not when you say, oh, quantum computers is gonna be the new stuff, it's gonna be the thing of the future, but then people come on and say, but it's not gonna replace classical computers. Well, kind of strange. So I look it up and try to understand it, and now I kind of see quantum computers are used to solve very specific tasks really, really efficiently and very fast. But certain tasks that are done by classical computers are actually very difficult for quantum computers. And to get to that, let's talk about how classical computers work a bit. Well, let's talk about the digital computers that hopefully we all have. If you own a machine per se that run calculations, that gonna be a computer, it computes something, right? And usually everything is stored as 1 and 0. We call it the binary system. And we store numbers, let's say 74, as a line of 1 and 0s. And the computers, before we have like 8-bit computers, 1 bit is one switch, 1 and 0. So 8-bit can store 2 to the 8 numbers in 1 byte, basically. And you can add that number that you basically the upper limit of the number you can store by having more bits. Modern computers, I think when we grew up, we still had to deal with 16 and 32-bit computer. Now, at almost every place use 64-bit computer, where there's 2 to the power 64 numbers you can store in one, basically one array, or one set of your bits, and that is quite powerful, right? You can have a lot of numbers. Well, but then what we can do with normal computers really well is storing those numbers and performing standard operations on them, like adding. Computers do adding really fast, so we have a bunch of bits and you add them, like 2 plus 2 equal 5. That is very fast.
If you want more information about how those computers work and how they're able to do those calculations, you can check out episode 46, which is where we talk about transistors and how they work, which are pivotal for classical computers to function.
And you could imagine designing a bunch of gates or operation. If let's say you can add really fast, then you can multiply really fast, because multiplication is adding. So you're adding multiple times, and computer is really, really good at repeating tasks. And if you tell them to do this in a loop, like over and over again, over different numbers, it's very, very fast. These days, even run to gigahertz, right? So billions of operation every second.
You're probably going to come to this later, so stop me if you are. But the other thing classical computers are really good at is retaining their states. I don't know how to... Basically, they're good at not... If I have a computer and I send if I send a message to my friend on the other side of the world, I say, hey man, what's going on? The message arrives and it says, hey man, what's going on? The text doesn't get all jumbled up and messed up due to different things like radiation from the sun or the wind, or all. It's good at retaining the state that you send messages in, because I'm not quite sure how to word this, but background noise doesn't really mess up classical computers very much. And that's the big problem with quantum computers, is that background noise, like thermal noise, whatever, it screws things up very much. So classical computers, you don't have to worry about that as much. And I think Patrick probably talked about that with the transistor episode, and I don't know.
Well, I think it's about the margin of error, right? Because if you try to determine if that bit is 1 or 0, well, if the signal come out 0.8, you say that's 1. I mean, 0.7 is still 1, right? But maybe if it's below 0.5, it's 0.3. We deem that to be 0. So if your voltage or your signal is affected by some noise, as long as it's not too much, you can still determine if it's 1 or if it's 0. So that is quite powerful. That's why we like binary system. We could make it tritary, tertiary. You have 3 or 4, but it makes it much more difficult to send signal, or it's more susceptible to noise. Okay, so that just classic computers, we design these transistors to perform operations, and we just feeding them numbers. And there's an upper limit to the numbers of things you can store, or you have to transfer things from memory. You store your number in memory, and then you can bring it out to do another calculation. And it's basically how classical computer works. And like the processing unit, CPU, the central processing unit, and there's like a graphical processing unit, are just different tools, but they are on the same principle of sending these numbers into some gates that do adding, multiplication and stuff, and give out another number. And that's what they do. So the difference is that the quantum computers don't only have 2 bits, or like two states. So not 1 and 0. Now you could say, well, then you have how many? Like, well, here's the thing. If you let's say you use spin as your state, it's up and down. I'm talking about like electronic spin, like electron spin in like particle spin. You can have up and down spin. So you can say, hey, maybe up is like 1, down is like 0. Maybe down is a ground state of the thing. However, then you gotta only have the 2 up and down, right? So with 2 pieces or with 2 switches, you have 2 bits, like classical computers. However, if you can entangle those bits in quantum entanglement, you can basically bind them in the quantum way together. So instead of having up and down, you can have up down and down up. So out of 2 bits, it acts like 4 classical bits, if you get what I mean, right? So, and that numbers goes up if you have entanglement. If you can entangle all your bits, and the numbers turn up to be 2 to the n, the number of qubit quantum bits is equivalent to 2 to the n power to the power of n of classical bits.
Yeah, a qubit's just a superposition of 2 classical bits, right? So you can have any, well, maybe not experimentally, but in principle, can't you have like any amount of each of them? So I could say like there's a 0.9 probability of 1 bit and a 0.1 probability of another.
Yeah.
There's this thing called the Bloch sphere
It
for the
doesn't matter.
physicists out there.
It doesn't matter. So what the point is that the 2 qubits can actually store. It takes 4 coefficients. Remember your quantum class, right? It takes 4 coefficients to describe it. So you can describe with 4 values. So you can use it to describe 4 values. And each of 4 values can act like a classical bit. It can act like a classical bit if you decided to store information. So if you have 100 classical bits, you get 100, 2 to the 100, right? But then if you have 100 qubits, you have 2 to the 100 classical bits, which can store 2 to the 100, so it scales up by a lot. However, the tricky part is that when it's entangled, here's the thing with classical bit, if I want to query, to ask, hey, what are the bits in between? What are the number of this? I can get any number I can, right? Because you just read the memory, you just do some math, you can figure out what the number that is. But the things that are stored under the entanglement, you cannot measure. Because when the wave function collapses, you only get, your ground state or the excited state. You get a random state. You get only one of the random one. You don't know exactly what all the numbers are, right? Because those are probability, or, probability would not be a complete description, I guess. Those coefficients are not measurable all at once. Let's say you have, 0.2, 0.3, 0.5, right? When you make a measurement, you only get a state you measure. You don't know about all the state that you have entangled. So that's what makes it difficult. So you have to devise a way so that you do some operation to your qubits so that your answer is measurable. And that is difficult. And so for classical computers, because all the bits are fixed and you know what they are, you can perform addition of an operation you want, and it's very deterministic. You know exactly what you're gonna get, and you get what you want. But with qubits, well, if you want to measure specific bits, you can't because it's just random and it depends on probability. So, but if you can perform operations so that your qubits will collapse or will be measured, what will be measured will be what you want. That is the challenge. So, and then, what's the point of storing, like having so many values stored or available to be stored? Well, now instead of storing, let's say to the 100, you can store many, many more, right? But then, well, instead of performing one operations over and over again to search for a solution, now you can take one big calculation, just one step, one very large step to search in the solution, or to search for the solution. Here's an example: encryption. So one of the concerns for quantum computers is that it's gonna break all our modern encryptions that we have right now. And the one that people like to use is called the RSA. If you do any secure shell, if you have to use your private key, public key stuff to be able to securely talk to another computer. And most of modern encryption is based on using primes, very large prime number. And those are, well, you get two really large prime numbers and you multiply them. So you get another prime number, or really, really, really big numbers, not necessarily prime. You get really big number. And to factor that, if it's just normal big number, it's pretty easy to factor. But if it's a product of two large prime numbers, well, then it's really hard to factor because there are only maybe 2 or 3 factors, and they're, most of them are primes, and it's really large. So it's really hard to guess. And that's how the solution space is really big. And classical computers can perform like addition and multiplication. So you can you can use some algorithm to try to solve that large number and factorize it. But it turns out it's really, really slow. And that's why we use it as an encryption technique to secure our messages, to secure our signal. We jumble them with this large prime that only you and the guy you talk to have the key, which is like we know which prime it is to use to solve that algorithm, solve the encryption, and we'll get the information we want. Because if you use the wrong prime, then everything will look like gibberish. So the problem in encryption, modern decryption, is just like solving big prime. Well, then because we only have a 64-bit system, 2 to the 64, not that many. If you use such a large prime with 300 digits or something, right? The number that classical computer can solve in one operation, in one loop, is like really, really little compared to what available, right? I think it's around 2 to the 300 or around that or something. So the number of loops required for classical computer to solve that is just, I think it takes millions of years to solve one. However,
yeah, I think you're about to say what I'm about to say, so I'll let you continue.
However, if each search is really big, right? So let's say there are 100 possible solutions, and if a classical computer can search 2 solutions at a time, it has to search 50 times to go over everything and find and the solution is 1 out of 100, right? So it might take 50 loops. But imagine a computer that can store 100 possible solution at the same time, and then do one algorithm to find one. But because they can store so many possible solutions, they can just run it. The step might be slow. You might take a slow step, but you only have to take it once. And I think that's the power of quantum computers. You hide the possible solutions in other dimensions that come from the entanglement. But however, like I said before, it's really difficult to perform operations. So you have to find a way to do it. And the way to do it to solve, there are multiple problems. I think they came out as like, hey, quantum computers might be good at solving this type of problem. And one of them is breaking the RSA or factoring primes. And the way they do it is actually not what I expected at all. It actually used the same algorithm as the classical computer. But that's one of the 4 steps, I think, that they actually accelerate so much. It basically make it trivial. Well, but to come up with that is not trivial. Yeah, there's retesting video on it I saw a while back and explain how it breaks quantum encryption. Well, but the short version of it is one of the problems is guessing the primes, right? Like what is the prime numbers that are the factors of that big number? And it turned out there's so many candidates, really difficult to do. But with quantum computer, they found what they call the QFT, which is not what Liam thinks. So Liam would think of quantum field theory, but this is the quantum Fourier transform. And I think we talked about Fourier transform before, but it's basically change your time domain into the frequency domain. So if you have something that's repeating, like let's say there's voice or sound signal or frequency wave, you Fourier transform it and you get a frequency out of it.
Yeah, it's this mathematical trick that lets you swap between the so-called conjugate variables. So in like sound design, if you record there's some famous example, but I can't remember it now, but basically, yeah, you can record time, so like you can record some song in time and then switch it to frequency. You can see like what frequencies were dominant and which ones they played. And there's some famous example where there was it might have been a Beatles singer, I don't know, but there was some singer who like swore during one of his performances because he made a note mistake, and some physicist went and like took his song and then Fourier transformed it and found out what words he said by finding the frequencies and matching the known words. But yeah, I've always wanted to know, because I always see in the literature there's a quantum Fourier analysis and stuff like that, and I always want to know what it is, because you use Fourier transforms in quantum mechanics all the time, but I don't think they're the same thing as quantum Fourier transforms. I think they're just still regular Fourier transforms that go between position and momentum space because of Heisenberg's uncertainty principle.
Well, I'm not going to talk about how it works, but I'm going to talk about how to use it. Well, basically, you do Fourier transform on all the bits and stuff, right? I think there's a paper on how it actually works. And, well, here's the thing. Well, the primes are still rational numbers. They are integers, right? And one thing we know about dividing rational numbers, it creates rational numbers or the fraction. Like basically, if you divide integers, you get rational numbers. That's I think a more proper way to say it. Any division or fraction of integers are rational numbers. Don't talk about zero. But here's the thing. What else do we know about rational numbers? Well, there's something that repeats. You can write it as fractions, and if it's less than 1, right? Every digit will repeat at the same period, really, right? If it's let's go 0.12121212, one repeats and two also repeats. And you can do that with any rational numbers. And it has a specific periodicity to it. And now, Liam, you guys probably see now how Fourier transform can be used. So if you can guess two prime numbers, there's some algorithm to it. And now you use the quantum Fourier transform to do some division and, with the big number, and you do a guess, you divide it, and you can pick out the periodicity when it repeats. So now you can know, I think, a digit of it, or a sample digit of it, and you use that to correct your qubit. But this algorithm basically exploit the power of rational numbers, that because you use integers as your solutions, and you multiply those integers. But if you divide the solution with one of the integers or a guess, there's a way to, and if you know the periodicity as those digits are repeated, you can use that to guess the number itself. And that's actually like a fantastic algorithm, really ingenious. So now the problem is well, how do you do it Fourier transform? So a guy came up with here, how to do quantum Fourier transform. So if you do that, and then you can get those two numbers that's close to the solution, and I think you can use classical computer algorithm to solve that really quickly. So the one to speed up is to find the guess of the close solution.
Yeah, that's really clever, because I guess when you go between like time and frequency domains with a regular Fourier transform, you're kind of exploiting the periodicity of sound waves, and here they to get a frequency, and they're just doing the same thing but with like numbers and digits. They're saying like, oh, if these digits repeat a bunch, then you that's like really clever, honestly.
Well, and the thing is that like they can do it with, like, I think the projection is that if you have 1,000 qubits, you can run almost all the numbers that are all the solutions that are possible at the same time, and then you only have to do that once, and then you get the answer. But now we only have less than like about 100 qubits or less, right? That's our current that we have right now, but it's going up. It looks like it's going up really quickly. So at some point we will reach that barrier where we can solve modern encryption in one go. And when I talk about modern encryption, it's anything that we have right now that are deemed secure, end-to-end encryption, that's gonna be gone.
Yeah, I think we talked about this before too, about how the number of qubits is increasing, but the big problem is that implementing this realistically is hard, because now, like, it's cool how all this very interesting physics, what it comes down to is that a calculation that a classical computer takes the age of the universe to do, a quantum computer can do it in like a few minutes or something stupid like that. It's crazy, and how it's just this fundamental kind of physics behind it. But then now you have to make a machine that does this, and that's the hard part. Because I think all these, like, you said that the number of qubits we're getting is increasing, but I think these are all like ultra cold, or maybe not ultra cold, but they're not room temperature setups. They're like very cold.
Well, I want to point out too that the opposite is true. That what could take quantum computers very long time to solve, classical computer can just solve immediately, right?
Mhm.
So they're specific too for specific purposes. Like, well, now you have a hammer, but you can use a hammer to screw your screws, but that's gonna take forever. Well, but you have screwdriver, and then if you want to use a screwdriver to hammer, it's gonna work, but it's gonna take a long time, right? So the mathematics is an abstract realm, right? And computer is one way to solve a problem. And you can say that, hey, maybe the other way you can solve the problem much quicker if you devise another method to solve it. That is what quantum computer is. That's why people say, hey, it's not going to replace classical computers, because the thing we want to solve with classical computers are still relevant and is still powerful enough to do. But certain things that classical computers are not good at, we can use quantum computers to solve it. And one of the problems turned out to be the encryption that we use. So I want to touch on how they are tackling that too. Well, we said before that quantum computers take advantage of the fact that entanglement can hold more information in their quote unquote dimensions. So you can basically hide a lot of values in the dimensionality. However, well, what we can also make encryption really highly dimensional. You can hide the answer in more and more dimensions than quantum computers have. So if you want to actually solve it, you have to use something that's not quantum computers. And I think the NSA or some organization put out a competition for encryption algorithm that could beat quantum computers, and I think when people send them in from all over the world, and they chose I think 4 out of it, because some algorithm were just beaten by just a PC. It's like, oh, it's really quantum computer safe, but a normal computer can beat really well. So we're trying to find an algorithm that is really hard to solve with both quantum computers and classical computers. And I can talk about one of them, which is I think Veritasium talked about too. It's actually, instead of prime numbers, using I think what's called the property of lattice. Because lattice is basically a repeating site, right? In the physics term. So if you have two vectors or that are not on the same direction, so two sets of complete bases, that doesn't have to be perpendicular. That doesn't have to be orthogonal or orthonormal. But if you have x and y pointing the way you want, you can create a lattice site as multiples of those x and those y's, right? And if I ask you, well, if I give you a point on a lattice or near a lattice site and ask you, well, how many times do I have to multiply each basis to get to that point? Well, that's kind of easy question in like 2-dimensional space. You just test out a bunch of vectors that you don't know and find a vector you know that give out the correct answer. Oh, try out the vector until you get the vector that give out the correct answer. But try do that in 3D. It's much harder to find the correct vector that actually get to that point in the same amount of steps. It's really difficult. And if you go the wrong way, you test the wrong way, maybe the correct solution is the vector that's point upwards. But if you test the one that points downwards, you're gonna go the wrong way. Well, then in 3 dimensions, there are more wrong ways you could go. Let's say 10 dimensions. Every step you try to find to test it, if you go the wrong way, maybe you never find a solution. And if you go to, I think, 11, 12 dimensions, even quantum computers gonna have a really difficult time. Because even though they can take a big step quite slowly, or it would be faster in future, even though they can take a big step, we just can make the dimension much more than what quantum computers have. So maybe for the normal encryption that we have, maybe it requires 1,000 qubits. Well, we just make a problem that you require millions and billions of qubits to be able to even have a possibility to solve it. And, well, how can we do that? When you say 10 to the 1,000, that sounds like a lot, right? Well, compared to what, right? Compared to 10, that's a lot. Compared to 2 to the 100, that's still a lot. But compared to infinity, it's nothing, right? It is very little part of infinity, because infinity is boundless. And mathematicians basically devise something to exploit this property of infinity that is boundless. So you just make the search space that you need to search close to infinity or really, really high. You can do that by adding more dimensions. And it's easy to solve in one or two dimensions. I think in physics we call it the curse of dimension, right? Oh, try solving in 3 dimension. Oh, it's really difficult. And try solving in 4 dimension. It's much more difficult. Well, but you can artificially add the complexity in terms of dimension to the system. So I can just make the problem 20 dimensions. Even quantum computers going to have a hard time solving it unless you're very clever about it. There's a way, I think mathematicians have a lot of ways to find solution from lower dimension and generalize. But so it's still not trivial to come up with those algorithms, right? So, but that's my last point, that even though our search of mankind or our algorithm can deal with very large number, the abstract numbers can just go to infinity, that you can always find a way to create algorithm or encryption scheme to use bigger and bigger search space. But if you actually know the solution, that is so easy. But if you don't, it's like, well, if you have a magnet, you can search pretty easy to find a needle in haystack, right? Well, but if I make a haystack like as large as the solar system, it's gonna be very difficult, even though you have this clever magnet.
I think the other one thing I just want to comment on is maybe for people who don't do science more so than others, but dimension doesn't necessarily mean like spatial dimension. Like, humans live in a 3D, well, we think we live in a 3D universe. At first glance, we live in a 3D universe. I can go forward, I can go left and right, and I can go left, I can go forward, I can go up. You have X, Y, Z axes, but in a computer, dimension's just some parameter or some specific quantity. So you can have, when you do like a computer calculation, or I don't know how to word what I'm trying to say, but you can have thousands of dimensions depending on what you're trying to do. So going past 1 and 2 dimensions is critical. Even though in principle, if you can do things in 1 and 2, like Felix said, it's easy. Once you ramp up the number, it gets super hard, depending. So I just wanted to point that out.
It's a combination of numbers, right? So there's nothing that limits us. So let's say I want to have, well, I mean, we can have 1,000 bits. There's nothing really stopping us. We just make it more complex for us to work with it, right? That's why we choose specific. We agree on specific number of bits, so everyone in the world can devise algorithm in the same language, in the same way, so we can talk to each other and we can develop it together. Like, there's no reason we have to choose base 10 for our numbers, but we do, right? Well, maybe because we have 10 digits on our hands that we have the base 10 numbers, but it's not necessary. We don't even use it for everything. Our time, when it gets to 60 seconds, it goes back to 0, right? So there's specific choice, but those are, well, there's nothing that really stop us from choosing the other one. So those are conventions. So a lot of mathematics have a lot of conventions that we agree on, that we have really, you can choose to have other things like the A4 is 440 hertz in music. Like, well, you can choose to be something else, like I do. But so today, I think that's a good place to end, unless people have lasting comments. And before we move on to the story, we'll get Patrick to tell us how to find us in this new 2024 year.
Well, first of all, I thank all of our people listening for listening in the new year. We're very excited for a year of a lot more podcasting. And if you are listening to us, you have found us already. But there are a lot of other places where you can find us. We have an email address if you would like to email us with questions or comments, or if you would like to be a guest on this show. We're hoping to have even more guests on the show this year than we did last year. So you can send us an email. We are hyperthesispodcast@gmail.com. You can also reach out to us and find us on Instagram. We are at the Hyperthesis, and there we post updates and some other fun things, such as our latest New Year's post. And you can listen or you can see all of our updated episodes and link to them there. You can also send us a DM with questions, comments, or if you are interested in being a guest on our show. If you would like to listen to us or share us, we are based out of Spotify, but we are found on pretty much whatever podcasting service you use, whether it's Apple Podcasts, Google Podcasts, Audible, wherever you listen to your podcast. And if you can, give us a rating or a subscription or download it, whatever you have to do with podcasting. We are also on YouTube. We are staying very much on top of our episodes, so you can check out our latest episodes there, as well as like, subscribe, and comment. And you can reach out to us over YouTube as well. So there are a lot of ways that you can reach us and you can listen to us. So feel free to share us. And if you have suggestions for episodes, or if you would like to be a guest and you are an expert in your field, now you could be a grad student or a professor or whatever you do, we would love to have you on the show. So moving on to wrap up today's episode is the story. Now, we spent some time talking about quantum computers and encryption and everything, and I want to take us back in time to introduce a person who is monumental in a lot of computer science. But to understand computer science today and to understand this person's impact, we have to go back in time over 200 years ago. So today's story is about someone who is incredibly important for computer science before computers were actually a thing. So this person is known as Augusta Ada King, Countess of Lovelace, who was born on December 10th, 1815, over 200 years ago. Now, her more common name, and you might recognize it, is Ada Lovelace. Now, originally, she was called Ada Byron and named after her half-aunt, and she was the only legitimate child of the poet Lord Byron, known as one of the greatest poets in England. Now, shortly after his daughter's birth, Lord Byron left his wife and child and separated from his wife before leaving England permanently, and he would never return before his death when Ada was 8. Now, Ada was left in the care of her grandmother for most of her upbringing and remained distant from her mother, but there was a lot of, expectations of people within their class. So her mother feigned interest in her child, but truly didn't have much to do with her. Now, during Ada's childhood, she was often ill, having many health challenges that left her incapacitated for extended periods of time. However, she was interested in mathematics and technology during this time, and she took advantage by doing her own research. And one of her first works actually involved the construction of wings. She had a fascination with flying and wanted to be able to fly. So she did her research looking at different materials and how they would behave, their strength and lightness, along with looking at different designs and basing the proportions and designs of the wings on the anatomy of birds. She even wrote a book called Flyology, detailing her findings. She was also tutored during this time, as one was in the high society of England, and even had an affair with one of her tutors at the age of 18. It was covered up after an attempted elopement, and they never ended up getting married. But this was, again, something in the high society of England. Now, as a member of that high society, Ada was introduced to many famous scientists and other public figures, such as Michael Faraday, Andrew Cross, Sir David Brewster, and Charles Dickens, the famous author. She was described as having a brilliant mind by many, and eventually went on to marry William, the 8th Baron King, at the age of 20, becoming Lady King. Now, some of these names might get confusing, so I'll try and keep track of them as best as I can. So at this point, she was Ada the Lady King. Now, she became Ada Lovelace when her husband was named the Earl of Lovelace, which had actually gone extinct. But Ada's line eventually could be traced back to Lovelace. And so her husband was given the title Earl of Lovelace, and she was given the title of Lady Lovelace. And this is where her last name, Ada Lovelace, came from. Now, before getting married and involving herself in a couple controversies, including some affairs and whatnot, she began a journey into mathematics, which would dominate the rest of her life. Now, we'll get into her short life, but she was most notably tutored by Mary Somerville, someone whom she greatly admired, and introduced her to a very pivotal figure in her life, Charles Babbage, who was a British mathematician and considered the father of the computer. She showed a lot of promise, learning calculus and other mathematics from her tutors that she would later use for her work that would lead to the prelude of computer programming. Now, the beginnings of her fascinations with logical systems began when she met Charles Babbage and saw his idea of what's known as a difference machine. Now, this difference machine was capable of calculating polynomials mechanically and was succeeded eventually by his analytical engine, which was a more general computer. Now, these are some of the first ideas of computers that came along, and the analytical engine in particular was designed to be a multi-purpose computer. So you could input values and receive output values, but it didn't have to be necessarily polynomials like the difference machine. It could be more general than that. And so the idea of a computer was actually sparked. Now, the interesting thing was he never actually built them, and only the difference machine was built, I believe, in 2002. So it took quite a while to actually get these built, and he didn't really get the favor of Parliament or any funding to have these machines built and tested. Now, this general purpose computer took the interest of people, particularly the Italian mathematician and former Prime Minister Luigi Menabrea, and he wrote an article that Ada Lovelace then wrote notes about. And within these notes, which were longer than the article itself, she was able to develop a working program for the device. And while, again, the device was never built, especially in Ada Lovelace's time, the code is argued to have worked on the machine and may be an example of the first computer program ever written. Now, there is some controversy in that, as Charles Babbage may have also written some computer programs, but it's generally regarded that if it's not the first one, it's among the first one that Ada Lovelace wrote. Now, she also wrote about many other things relating to computers, such as artificial intelligence, a topic that's very in demand right now, but she denounced it and actually received rebuttals from it by people like Alan Turing many years after her death. Now, although her work is remembered in mathematics and computer science, she was also into different scientific fads at the time. For example, phrenology, which is studying the surface of the head, and mesmerism, which is the theory that all living things have some sort of force connecting them. She also wanted to develop mathematical models for how the brain works, and attempted to develop models for winning bets and gambling games. So she actually developed a syndicate based on these mathematical principles that she thought would work out, and she would win a lot of money, ended up losing a lot of money, owing the syndicate she created a lot of money, and then eventually got her husband involved to help fix things. So maybe not the best bet to pull that move, although I believe people from MIT saw that was a bit more successful later on. Now, she did not live a very long life filled with mathematics, and she died at the age of 36 on November 27th, 1852. She died of uterine cancer after a very lengthy battle, and was buried next to her estranged father at her request. Although he had died when she was 8 and she never truly met him, she admired him and defended him throughout her life. Now, Ada Lovelace's legacy is monumental for someone that was involved in some of the first computers. And there are many different computer-related names and awards that are named after her. For example, there's a programming language called Ada that was created on behalf of the United States Department of Defense, and many awards have been named after her. If you happen to be listening to this in Britain, and you have a passport that was made after 2015, you'll actually find a picture of Ada Lovelace and Charles Babbage inside. So she was a very impactful woman in high society, and her legacy still lives on today. And it's very interesting to read about the different theories that she had.
All right. Thank you, Patrick, for the story for today. And well, that's the end of the episode, the first of 2024. My explanation might a little bit be convoluted from time to time, but hey, it is what it is. All right. Well, I'll talk to you guys next week. Take care.
Bye, everyone.
See ya.